Hello, students. I hope you all are doing good. So, in yesterday's lecture, we have discussed mutual induction. Okay, in today's lecture, we are going to discuss the self-induction. Okay, we have studied about two type of induction or inductance. That is mutual inductance and self-inductance. Mutual we have discussed in detail yesterday, and today we are going to discuss self-induction and self-inductance. Okay, so the topic that we are going to discuss is NCERT section 6.7.2 and example 6.9. So this is the disclaimer. Learning objectives. After this lecture, you will be able to calculate and understand the self-inductance of a solenoid using its physical parameters and analyze how induced EMF opposes changes in current. So this is the index of topics that we are going to discuss today is NCERT section 6.7.2 self-inductance and example 6.9. We are also going to discuss one additional example also. So let's start with self-induction. So what is self-induction? So it is the phenomenon where an EMF is induced in a single isolated coil due to a change of current in the coil itself. Okay, in yesterday's lecture, what was mutual induction? It was induction of EMF, or we can say EMF is induced in one coil due to change in current in the another coil. There were two coils. In self-induction, EMF is induced in a single isolated coil. It is not in the influence of other coil or not placed nearby another coil. Only one coil is there. Okay, so EMF is induced in a single isolated coil due to change in current in the coil itself. Current is flowing in the same coil and EMF is induced in the same coil also. Okay, what will be the direction of induced EMF? We are going to discuss it. Okay, it will be in accordance with Lenz's law. So what is self-inductance? Self-induction is the phenomenon. Self-inductance is the property. It is a property of coil that describes how a change in current in coil induces EMF in the same coil. Okay. So this is the diagrammatic representation. Okay. So you can see in the diagram, key pressed in the first diagram. So key is pressed. So when key is pressed, current will start increasing from 0 to I. Okay, we have discussed this thing, tapping key experiment. Experiment 6.3, Faraday's third experiment. Okay, so this was tapping key. So when key is tapped, current increases from 0 to I in very, very small time, in milliseconds or we can say microseconds. Okay, so that for that small time, for that amount of small time, current is changing from 0 to maximum value. Okay, due to this change, this coil, due to the change in the current in this coil, EMF will be induced, and this is called this phenomenon is called self-induction, and it is a property, and this properties of this coil is called self-inductance. The property of this coil to induce EMF when there is a change in current through this coil is called self-inductance. Okay, so current is increasing, so this coil will induce EMF. The direction of the induced EMF will be according to Lenz's law. It will oppose the cause that is producing it. Okay, so what is the cause here? Cause is increasing current. So it will oppose the increasing current. It will try to decrease the current. Okay, so the direction or polarity of EMF will be in the opposite direction. Okay, so this thing, direction of this EMF represents that positive terminal of the battery we can assume here and negative here. Means direction of current will be, this is the direction of current actually, and polarity of EMF. Polarity of EMF means positive terminal will be on positive terminal, hypothetical positive terminal. Okay, induced EMF. It is induced EMF. So there is no actual positive or negative terminal, but we are theoretical. In theoretical way, we can draw on the left side positive terminal, on the right side negative terminal, and direction of current is induced current will be shown by this arrow. It will be opposite to the increasing current. So it will oppose the increase in current. Okay, so what is the cause of the EMF induction? EMF is inducing. What is the cause? Increasing current. So the induced current will be in opposite direction to the increasing current. Okay, so current will be, or EMF will be induced to oppose the cause, that is increasing current. Okay, now in the second case, now we have released the key. Now current will decrease from maximum value to 0 in very small time. Due to that small time, current will be decreasing in this coil. So current is decreasing, due to which the coil has the property to oppose the cause, that is producing EMF. So EMF will be produced, and direction or polarity of EMF or direction of induced current will be such that it will oppose the cause. What is the cause? Decreasing current. Okay, so why the direction of induced EMF or current is same as decreasing current? Because it will be in the same direction. It will oppose the decrease of current by producing additional current. Current is induced, it is supporting the decreasing current to stop the change in the current, to maintain the same amount of current in the circuit. And this, in the first case, this induced current is trying to oppose the change in current to maintain the same amount of current, to oppose the increase. It is opposing the decrease. So it is supporting it is in the same direction of decreasing current. So it is trying to stop the decrease of current by providing extra amount of current in the same direction to avoid any change in the current. Okay, that's why it is in same direction, it is in opposite direction. Okay, understood? So direction of EMF, or we can say polarity of EMF, is such that it will oppose the cause. So this is the property of self-inductance. So self-inductance is a scalar quantity. As mutual inductance was scalar quantity, self-inductance is also a scalar quantity. SI unit is Henry, that is H. So consider a coil having N turns and current I flowing through it. So you can see the coil. Okay, so this is a coil having N number of turns and current is flowing through this coil. Okay, so figure showing current carrying coil and it is having N number of turns. So magnetic flux phi B through the coil is proportional to the current I flowing through it. Okay, so we know that magnetic flux is proportional to current. Why current? Because current is proportional to magnetic field is proportional to current. That magnetic field lines, that magnetic field through this coil is proportional to current flowing through it, and that magnetic flux is proportional to the magnetic field. Okay, so by this relation, magnetic flux is proportional to the current flowing through the coil. Okay, so that is phi B is directly proportional to I. So flux linkage with the coil. Now we know that this phi B is magnetic flux through one turn. The flux linkage is magnetic flux through all the turns, considering all the turns of the coil. So flux linkage with the coil will be N phi B, which is equal to Li. So after removing this proportionality sign, this L will appear. Okay, so this L is constant of proportionality. Like we have discussed in yesterday's lecture also, in mutual inductance, what was the proportionality sign? M. Okay, now in case of self-induction, or we can say self-inductance, constant of proportionality will be L. Okay, and mark it as 6.13 equation, where L is the self-inductance, or we can say coefficient of self-induction. Okay, we can call it coefficient of self-induction or self-inductance, okay, of the coil. If current I of the coil changes, an EMF is induced in the same coil. Okay, so this is the property of self-inductance. So EMF induced will be minus dN phi B upon dt. Okay, that is the relation by using Faraday's Lenz's law. Okay, EMF is equal to rate of change of magnetic flux through a coil. Okay, and negative sign indicates the polarity of the EMF, which is equal to, what is N phi B? We have seen Li. So put Li in place of N phi B, it will result in minus d by dt Li. So epsilon is equal to minus L. L is constant of proportionality. It will come out of derivative. So minus L di by dt. Mark it as 6.14 equation. The self-induced EMF, or we can say, so this EMF that is induced in the same coil in which current is changing. So this is self-induced EMF, or we can say back EMF. Okay, in this case, in case of self-inductance, that induced EMF is called back EMF also. Okay, opposes any change in the current, increase or decrease in the coil. So it will oppose any change in the current. Okay, either it is increase in current, either it is in decrease in current of the coil. Okay, so self-inductance L of a coil is numerically equal to the EMF induced in the coil when the rate of change of current through the coil is unity. Okay, so from here we can define this constant. So this self-inductance L of the coil is numerically equal to the EMF when this di by dt will become 1. That means the rate of change of current through the coil will become unity, means 1. So then this L will be equal to epsilon, numerically equal to epsilon. Okay, ignore this negative sign because it is only showing the polarity of the EMF. If we take magnitude, then this L will be equal to magnitude of EMF induced. Okay, so physical significance. What is the physical significance of self-inductance? It plays the role of inertia in electricity. Okay, we have discussed in chapter force in 11th chapter, in 11th class, chapter force. Okay, in that chapter there was in motion. Okay, in kinematics we have discussed inertia. Okay, before Newton's first law of motion, we used to discuss inertia. Okay, so that is inertia in mechanics. So inertia in electricity, self-inductance plays the role of inertia in electricity. Why it is called inertia of electricity? Because it is opposing any change of current through the coil. And in mechanics, what was inertia? So what was inertia in mechanics? It was opposing any change in the direction of motion, in the state of rest or uniform motion. So it was also opposing something in mechanics. And in electricity, what is it? Self-inductance. It is inertia of electricity. So it opposes the growth of current when circuit is switched on and opposes the decay of current when it is switched off. Got it? When we switch on, when we tap the key, it opposes the growth of current. When we release the key, it opposes the decrease of current. So self-inductance of a long solenoid. So consider a long solenoid of length L, cross-sectional area A, and n turns per unit length. So this is the coil having n number of turns, current I is flowing through it, and length of this solenoid is L. Okay, figure showing current carrying solenoid of length L. So total number of turns So small n is turns per unit length. So capital N will be small n into L. When a current I flows through the solenoid, the magnetic field inside is given by B equal to mu naught Ni. Okay, that thing we already know, that for a long solenoid, magnetic field inside the solenoid is given by mu naught Ni, where I is current flowing through it, small n is turns per unit length. Okay, so flux through a single turn, that is phi B, which will be equal to Ba, that is equal to mu naught Ni A. B we have calculated, that is mu naught Ni into A. Total flux linked with the solenoid N phi B is equal to NL into mu naught Nia. Okay, so what is flux? We have calculated mu naught Nia, and total flux linkage is this phi B is flux linked to a single turn, and total flux linked with the solenoid is N into phi B. Okay, so N is small n into L. So N phi B is equal to, after simplifying it, N phi B will be equal to mu naught N square A L and into I. Now flux phi B is related to self-inductance L of the coil by the relation equation 6.13. So this thing N phi B is equal to Li, we have discussed in previous slides. Okay, so N phi B is proportional to I, so phi B is equal to, or we can say N phi B is equal to Li. Okay, so we can put this N phi B equal to Li in this equation. Okay, so we will get the expression for self-inductance. So comparing the expression for N phi B, we get Li equal to mu naught N square Al into I. So I and I will get cancel out. So L will be equal to mu naught N square Al. We have also discussed these expressions of mutual inductance in yesterday's lecture. Okay, and we have proved that M21 and M12 are equal by this thing. Okay, but here only one L is existing because only one coil is there. Okay, so I and I will get cancel out. So L will be equal to mu naught N square Al. Mark it as 6.15. Okay, the self-inductance of the coil depends on its geometry. So what are the conclusion from this final expression? That this self-inductance depends on the geometry of the coil, that is area, length and number of turns per unit length, and permeability of medium. Here we have taken only free space inside the core of the solenoid. Okay, but if we are inserting any medium of relative permeability mu r, then this self-inductance will change. So it also depends on the permeability of medium. If the solenoid is filled with the material of relative magnetic permeability mu r, then L equal to mu naught mu r N square Al. Okay, if we are filling the solenoid core with any material of magnetic permeability mu r, then this is the expression for self-inductance. Mark it as 6.16 equation. So L will be equal to mu N square Al. Okay, this mu naught into mu r will be equal to mu. This is the relative permeability of medium. Permeability of medium. That is permeability of free space, and mu r is relative permeability of medium. Okay. So energy stored in a circuit. Self-induced EMF opposes any change in the current in the circuit. That thing we have discussed. To establish a current in the circuit, work must be done against the back EMF. Okay, so what is the energy stored in the circuit? The circuit which is containing the coil or solenoid. Okay, so energy will be stored. Which energy? Magnetic potential energy. Okay, we have discussed in the case of capacitor. When capacitor is connected in the circuit, which type of energy is stored? Electrostatic potential energy due to the capacitor. Now we are connecting coil, or we can say solenoid, which is also in the case of self-inductance and this coil having n number turns, it is called inductor also. Okay, that component we are going to use in next chapter, alternating currents. Okay, that is called inductor. A coil having n number of turns closely wound is also called inductor. Okay, so self-induced EMF opposes any change in the current in the circuit. So when there is a change in current in the coil, then there is EMF will be induced in the circuit in the coil. Okay, so that will oppose the change in the current. So to establish the same current, it is opposing the current. To establish the current in the circuit, so we have to do some work against the back EMF. This induced EMF, also known as back EMF. Okay, so it is trying to oppose the change in current. So to maintain or establish a steady current in the circuit, work must be done against the back EMF. Amount of work done against the back EMF is stored as a magnetic potential energy in the circuit. So that amount of work we are doing externally against the back EMF, okay, to establish the steady current in the circuit, is stored in the circuit as magnetic potential energy. Okay, so back EMF of circuit is given as epsilon equal to minus L di by dt. That thing we have calculated. Okay, so for the current I at any instant in a circuit, instantaneous power required to overcome the back EMF is for the current I at any instant in circuit, instantaneous power required to overcome the back EMF is P equal to epsilon EMF I. Okay, so we also know in from current electricity that power is equal to VI. Okay, so now we are going to provide external power that will oppose the effect of induced EMF. Okay, so we have to provide the same amount of power as induced EMF is providing. Okay, so EMF is induced, current is induced, due to which there is some power of induced current. So we have to provide the external power equal to that induced power, so that the effect can be nullified. Okay, so we have to do the work against the back EMF. We have to provide the circuit same amount of power to nullify the effect, to establish a steady current. So for the current I at any instant, so for any instant there is I current in the circuit, so instantaneous power required to overcome the back EMF will be equal to P equal to epsilon I. So if we ignore the resistive losses and only consider only inductive effects, okay, we are not considering the resistive losses. That means that that coil is made up of some material, and this material has will have its own resistance, but we are not taking resistance here. We are taking EMF due to only inductive effects. That induced EMF is due to only inductive effects. We are not taking potential drop due to the resistance of the coil. Okay, we are neglecting it for now. So we ignore the resistive losses. We are ignoring the potential drop due to the resistor. Okay, so we are ignoring resistive losses, only considering the inductive effects. That is that effect due to which EMF is induced. Then using equation 6.14, power will be equal to L di by dt. This is the induced EMF, taking magnitude of induced EMF into I. Okay, so small amount of work done dw in time dt is dw equal to p dt. Okay, so we know that work done is equal to power into time. Okay, so small work done is equal to power into small time dt. So dw will be power into dt. So power is L di by dt into I. So Li di by dt into dt. So dt and dt will get cancel out, and we will get dw equal to Li di. So total work W done in establishing the current from 0 to I is. So total work done will be equal to integration dw equal to 0 to I Li di. So L is constant, it will come out of the integration. So I di, integration of I di will be I square by 2, and limits 0 to maximum current that we are going to establish steady current I. So putting the limits, so I square by 2 minus 0. So work done will be equal to half Li square. Mark it as 6.17 equation. So this work done is stored in the form of magnetic potential energy UB of the circuit. So magnetic potential energy will be equal to half Li square. So this is the final expression for magnetic potential energy that is stored in the circuit. And that potential energy is due to the work done. That work done we are doing externally to maintain the steady current in the circuit. This expression reminds us of mv square by 2. So mv square by 2 is expression of for the mechanical kinetic energy of a particle of mass m, and this is half Li square. This is half mv square. So that means that L is analogous to this m. Okay, we have already mentioned that this is inertia of electricity, and the inertia and mechanics is due to this mass is the measure of the inertia and mechanics. More mass, more inertia. Less mass, less inertia. Okay, so this L is analogous to this m. So it shows that L is analogous to m. That is, just as mass resists change in motion, that is called inertia. Due to the mass of the body, it resists change in motion. Okay, inertia is, this mass is measure of this inertia. So mass, due to the mass, body resists changes in motion. So self-inductance opposes changes in current flow within a circuit. So that means L is analogous to m if we are comparing this relation with this by drawing analogy. Now consider the general case of currents flowing simultaneously in two nearby coils. Okay, now in mutual induction we have discussed that only current is flowing through one coil. We have taken two cases. Okay, we had taken two cases in yesterday class. Either current is flowing through outer coil, either current is flowing through inner coil. Okay, but consider the general case. Then current is simultaneously flowing through two nearby coils. Okay, the flux linked with one coil will be the sum of two fluxes which exist independently. Now, flux linked with any coil will be due to the current flowing through other coil and due to the current flowing through it itself, through its own itself. Okay, means now mutual induction will be there, self-induction also will be there. Okay, so magnetic flux linked with one coil will be sum of two fluxes which exist independently. Therefore, equation 6.7 would be modified into, so we have discussed equation 6.7, that was N1 phi1 equal to M1 to I2. Okay, but now due to current flowing through it, through the same coil through which we are going to calculate the flux, the current is flowing through that coil also, through the same coil also. So due to the current flowing through the same coil also, there will be another term due to the self-inductance, that will be M11 I1, that is mutual induction of first coil due to the first coil. That thing we have discussed in the mutual induction. Current is flowing through second coil and flux linkage with the first coil will be mutual inductance of first coil with respect to second coil and current flowing through second coil. Now current is also flowing through first coil. Both coils, in both coil current are flowing simultaneously. Okay, so M11, this M11 representing mutual inductance of first coil with respect to first coil. That means it is self-inductance. Any inductance that is linked with one coil with respect to that same coil, that is self-inductance into I1. I1 is the current flowing through first coil. Now this equation has been modified. So where M11 represent inductance due to the same coil. Using Faraday's law. Now using Faraday's law, this epsilon 1, this EMF induced in the first coil will be equal to minus M11 di1 upon dt minus M12 di2 upon dt. Okay. Now M11 is the self-inductance and it is written as L1. Therefore, the EMF induced in the first coil will be minus L1 di1 upon dt minus M12 di2 upon dt. Okay, in yesterday's class we have discussed that epsilon 1 EMF induced in the first coil due to the current flowing through another coil will be equal to minus M12 di2 upon dt. That thing only. That thing we have discussed. Now current is flowing through the same coil also, due to which self-induction, or we can say self-inductance, also came into play. So this expression for flux linkage and EMF induced will be modified accordingly. Got it? Now example 6.9. A part. Obtain the expression for the magnetic energy stored in a solenoid in terms of magnetic field B, area A and length L of a solenoid. And B part. How does this magnetic energy compare with the electrostatic energy stored in the capacitor? Okay. So in first part, you have to calculate the magnetic energy stored in a solenoid and measurements are given. And in another B part, you have to draw the analogous with magnetic energy to the electrostatic energy. Okay. Now A part. Magnetic energy stored in a solenoid is given by equation 6.17. So magnetic energy UB will be equal to half Li square. That thing we have discussed, where I is the current flowing through the solenoid and L is self-inductance of the coil. So self-inductance of solenoid will be L equal to mu naught N square AL. Okay, you have to find the magnetic energy stored. We know the expression, that is half Li square. But in the terms of magnetic field B, in the term of area and length only. Okay, so we know that expression for self-inductance is given by L equal to mu naught N square AL. Equation 6.15 of NCERT, where mu naught is permeability of free space and N is the number of turns per unit length of solenoid. So magnetic field of solenoid B equal to mu naught Ni. So from here we can calculate I is equal to B upon mu naught N. Now put the values of L and I in the equation of magnetic potential energy. So UB will be equal to half Li square. So L will be mu naught N square AL and B will be I will be B upon mu naught N. Okay, so it will result in equal to half AL B square upon epsilon naught after solving it or simplifying it. So UB will be equal to, in terms of B, A and L, UB will be equal to half B square upon mu naught into AL. This AL is the volume of the solenoid, area into length. Now B part. Magnetic energy of a solenoid is UB equal to half B square upon mu naught into AL. Okay, volume of the solenoid is given by V equal to AL. Magnetic energy per unit volume is small ub equal to capital UB upon V. So magnetic energy per unit volume. So it will be a ratio of magnetic energy upon volume of the solenoid. So small ub, that is magnetic energy per unit volume. So equal to UB, capital UB upon V, which is equal to capital UB upon what is the volume of solenoid, AL. So small ub will be equal to, so capital UB, magnetic energy, magnetic potential energy is half B square upon mu naught into AL. So dividing it by AL, it will result in B square upon 2 mu naught. Mark it as 6.18 equation. Another equation. It is also known as energy density. Magnetic energy density. Okay. So electrostatic energy stored per unit volume in a parallel plate capacitor is given by. So we have discussed in the electric potential and capacitance chapter. Okay, equation 2.73. Okay, according to that, electrostatic energy stored per unit volume in parallel plate capacitor is given, which is equal to UE is equal to half epsilon naught capital E square. Okay, so that E is electric field. This is the electrostatic energy stored per unit volume in the plates of capacitor. Okay, so where epsilon naught is permittivity of free space and capital E is electric field of a parallel plate capacitor. Now you can see we have discussed UB is equal to half B square upon epsilon naught, mu naught. Okay, so UB is that mu naught is constant, half is constant. So that magnetic energy density UB is proportional to B square. Now here electrostatic energy density is proportional to capital E square. So in both magnetic and electric fields, the energy stored is proportional to the square of the field strength in both cases. So equation 6.18 and 2.73 have been derived from special cases, that is a solenoid and a parallel plate capacitor respectively. But they are general. These expressions are general and valid for any region of space in which a magnetic field and an electric field exist. These results are not only applicable for solenoid and parallel plate capacitor, they are general results and valid for any region of space in which a magnetic field and an electric field exist. Okay, so another additional example is there. So A part is what is the self-inductance of a solenoid of length 50 cm, area of cross section 20 cm square and 500 turns. B part is a current of 2 ampere is passed through it. If the current is reversed in 0.1 second, what is meant by reversed? Means magnitude remains same but direction of current is changed. Okay, so what is the average EMF induced? So let's see the solution. So what is given? L equal to 50 centimeter, that is equal to 0.5 meter. Area is equal to 20 centimeter square, that is 20 into 10 power minus 4 meter square. Capital N is equal to 500. Turns per unit length, small n is equal to, so we have to calculate turns per unit length also. So for to calculate the average EMF, so small n is equal to capital N upon L, that is 500 upon 0.5, which is equal to 1000 turns per meter. Okay, so these are given things. Now A part, self-inductance of a solenoid is given by L equal to mu naught n square AL. Okay, if you are using capital N in place of n square in the expression, then what you have to do? Put this value of n small n is equal to capital N upon L. So it will result in capital N square upon L square. So L square in the denominator and L in the numerator. So one L will get cancelled out. So it will result in mu naught capital N square A upon L. This is also valid expression. Okay. But if you are using small n, then expression is like that. L equal to mu naught n square A L. That L will go in denominator if we are using capital N, only number of turns. But if we are using number of turns per unit length, then that L will be in numerator only and nothing is in denominator. Okay, so mu naught is the permeability of free space and mu naught is equal to 4 pi into 10 power minus 7 Tesla meter per ampere. So L, after putting all the values, so L will be equal to 4 pi into 10 power minus 7 into that N is 1000 turns per meter, so 1000 square into what is A, 20 into 10 power minus 4, and what is length, 0.5 meter. So L will be equal to 4 pi into 10 to the power minus 7 into 10 to the power 6 into 20 into 10 to the power minus 4 into 0.5, which will be equal to 4 pi into 10 to the power minus 7 into 10 to the power 3. So that is the calculation part. So L will be equal to 1.256 into 10 to the power minus 3 Henry, which is equal to 1.26, after approximating, 1.26 millihenry. Now B part. Initial current. What was the initial current? 2 ampere. Okay, now current is reversed. Magnitude is same but direction is reversed. So final current will be equal to minus 2A, minus 2 ampere. So change in current will be I final minus I initial. So minus 2A minus 2A minus 4A. So time interval will be equal to, what is the time interval given? Current is reversed in 0.1 second. So delta T will be equal to 0.1 second. Now induced EMF in the solenoid will be epsilon equal to minus L. Why there is not di by dt? Because there is large amount of change in 0.1 second. Okay, so time interval is not so big, but change in current is big. Okay, so that's why delta is used. So we can find the induced EMF by using we can use the in expression delta also, d also. So when di by dt is used, means small change in current in a very small interval of time. Okay, so, or we can say in very small interval of time, in microsecond, in millisecond. But here 0.1 second, it is not so small interval, and also change in current is large, so delta is used. It is also correct, valid expression. So epsilon is equal to minus L delta I upon delta T. So after putting the value of delta I, delta T and L, so minus 1.26 into 10 to the power minus 3. So L we have calculated in A part. Okay, and into minus 4 upon 0.1, which is equal to 1.26 into 10 to the power minus 3 into 40 volt. So epsilon will be equal to 50.4 into 10 to the power minus 3 volt, which is equal to 50.4 millivolt. Okay, so this is the induced EMF in the solenoid. So let's look upon summary. So self-inductance is the property of an inductor that causes it to oppose any change in the current flowing through it by inducing an EMF in itself. When current through a coil changes, the magnetic flux linked with it also changes, inducing a self-induced EMF E equal to minus L di by dt, where L is self-inductance. Okay. When current changes in the conductor, it creates a changing magnetic field, which then induces an EMF in the same conductor, that is called self-induced EMF. The formula used is L equal to mu naught n square A upon L. That thing I have mentioned already. If you are using capital N, that is number of turns only, then L will go in denominator. So both are valid expressions. So capital L is equal to mu naught n square A upon L, where mu naught is permeability of free space, capital N is number of turns, capital A is cross-sectional area, and small l is length of solenoid. The energy stored in an inductor is given by the formula UB is equal to half Li square, where L is the self-inductance and I is the current flowing through it. There are some practice questions you have to do yourself. So what is self-inductance? Define it and state its SI unit. A coil has self-inductance of 5 Henry. If the current through it changes from 2 ampere to 0 ampere in 0.1 seconds, calculate the induced EMF. An inductor of 2 Henry carries a current of 0.5 ampere. Calculate the energy stored in the magnetic field. Why does an inductor oppose sudden change in current? So what is inductor? It is similar to coil having n number of turns and wound closely. State the formula for energy stored in an inductor and explain each term. Okay, so this is all about today's lecture, but we have to do the DPP. Okay, first question. The self-induced EMF in a coil opposes any change in the current. The phenomenon is analogous to which concept in mechanics? So write your answers in comment section. Which option is correct? Frictional force, gravitational potential energy, inertia of mass, or electrostatic potential energy? Which option? A solenoid with self-inductance L carries a current I. The magnetic energy stored in the solenoid is half Li square, Li square, or half I square by L. Yes, second option. A solenoid of length L, cross-sectional area A and N turns per unit length is filled with the material of relative permeability mu R. If the current through the solenoid is I, what is the self-inductance of the solenoid? Yes, second option. Two coils are placed nearby. The EMF induced in the first coil due to changing current in the second coil is given by epsilon 1 equal to minus M12 di2 upon dt. What does M12 represent? Self-inductance of the first coil, mutual inductance between the two coils, resistance of the second coil, capacitance between the two coils. So this M12 is what? Self-inductance, mutual inductance, resistance, or capacitance? The magnetic energy per unit volume inside a solenoid with magnetic field B is given by. So magnetic energy per unit volume, energy density, B square upon 2 mu naught, B by mu naught, half mu naught B square, or B square by mu naught. Which option is correct? Yes. So well done. All the answers are correct. Okay, I hope you enjoyed the session. Thank you.